So in previous videos, we've already talked about how to add an alcohol to the more substituted carbon, like so, with either oxymercuration or a direct hydration. We talked about how to add it to the less substituted carbon with hydroboration, followed by oxidation. So in this case, we're going to talk about how to do both, to add alcohol groups to not one but both of the two carbons of an alkene. And the most direct way to go about that is to use a reagent called osmium tetroxide. And that has quite a few issues with it, and we'll go through them as we go into this topic. So first, how does it work? Since we don't have different groups being added, we don't have to really consider regiochemistry. Both carbons are getting an OH, so we don't need to worry about looking at an asymmetric example. We do, however, have to deal with a stereochemistry issue. This is a syn addition, so remember what that means. We're adding to the same face, and it means synchronous, and we're adding at the same time. So here is how it actually works. It is the first example that we're going to talk about of what is known as a cycloaddition. And that is a topic we'll cover in a lot more detail when we get to the dienes chapter, which is the beginnings of Orgo 2. But this is the first example we're going to deal with it, and it involves basically electrons moving in a circle, so hence the cycloaddition part, that we're going to have a couple of things happening. We're going to have one, what is no real way to tell direction here, because everything is, the electron flow is in a circle. So what happens first and what happens second here is really difficult to determine. So we're going to have a problem like this, that we're going to end up with the two O's on the same face of the alkene, because it's the only way we could do it. They can't wrap around to the other side. If you tried, it's too far of a distance to have things add to opposite sides at the same time. So at the beginning of this reaction, this is osmium 8, and after the first step here, it has gone down to osmium 6. Now, the removal of this, we're going to talk more about as we move along, but basically, this gets hydrolyzed off. So we're talking about, in some cases, I've seen it written with just water. Usually, it's water and some relatively mild acid. And what we get is this. We get the alcohols here. And although it's not usually written this way, I did find it in one book. Osmic acid, which is this. There are a couple of reasons why it's not usually written that way. First, this is as far as your book takes it. They basically cop out on how the hydrolysis works, how we go from this top right structure, this cyclic osmate ester, to the diol and the osmic acid. I'm not a big fan of copying out on things like that. So there are a couple of problems with it. Let's go through them. One, this reaction as written is enormously expensive. To put that in context, at the time of this writing, 1 gram of gold, sorry, let's try that again. 1 gram of gold is selling for something like $52.75 per gram. Platinum, a little bit less expensive at the moment. So at $24 approximately per gram, I saw a couple of different sites. $23.56 actually is the one I wrote down, so we'll keep that. 1 gram of osmium tetroxide, and this is considered a bulk purchase from the company we normally have to buy things from, which is Aldrich Chemical, on small scale. They service small scale laboratories like us, primarily, is $348 a gram. So you can think about this as basically, gold plating your reaction and having lots of money left over. This is, 6 times more expensive than gold. So it is an enormously expensive process, and we're talking about a gram. If we use the stoichiometry the way that it was written originally, like this, a 1-to-1 mole ratio, this reaction is basically unusable. It would be too expensive to have any preparative use. So we really wouldn't want that. It is actually a very, very mild reaction. It's easy to perform, and it does a very good job selectively of working with alkenes in the presence of alkynes. There's a lot of good reasons to use this instead of some of the other options that are out there, but the expense is enormous. So first, we're going to have to get it back from that leftover osmic acid, which is written a couple different ways, but to the usable osmium tetroxide. And that's actually not as hard as it sounds. And if we could do that, well, then we've set up a catalytic cycle where it can come back in. So that's the next piece of the puzzle here. How do we do this? So the current conditions look like this. The ones that are used more commonly, we're using osmium tetroxide. As our mild acid, we're using the monopotassium salt of sulfonic acid. So potassium bisulfite. This is just a mild acid. It's a weak H3O+. That's all we really need to think about it there. That takes care of the hydrolysis, but it doesn't give us anything else as far as getting the osmium back where we want it. So the osmium needs to be brought back from osmium 6 to this osmium 8 that we use at the start of the reaction. So we need something that's going to react with the metal and not really react with our substrate as it is. What we generally use for that now is something called NMO, which stands for N-morpholine N-oxide. And it looks like this, that we have a heterocyclic ring, which we haven't really dealt with much of that yet at this course. We'll deal with a lot of that in the next course. It has an ether at the top and an amine at the bottom. This, if I just have a hydrogen here, is morpholine. But this is the oxide, so it has an ionic oxygen here and therefore a cation on the nitrogen. If I use that, what it does is takes me from osmium 6 back to osmium 8. So I get back my oxidant. So this allows us to take down the amount of osmium tetroxide we need from a 1-to-1 mole ratio to something more like 100 to 1,000 to 1 mole ratio of alkene to osmium. So basically, instead of gold plating your reaction and having money left over, now this becomes literally like just chump change. It becomes much more affordable. That 1 gram that we talked about as pricing could do hundreds and hundreds of grams of alkene oxidation and being reused. So it's enormously useful in that we can reoxidize it back to the osmium 8 state the way it needs to be. So let's look at that hydrolysis very quickly, because I really don't like cases where we don't get an answer on how things work, and your book has done that, as have most textbooks. So here's that cyclic osmium ester, the cyclic osmate ester. And basically what's happening here is the functional equivalent of just acid and water. So just this and this. Now, normal esters, if we have something like this, and we treat it with acid and water, we will hydrolyze that. So if I did this with the right pH of acid, strong enough of an acid, I'll get an alcohol and I'll get a carboxylic acid. So this is a reaction of carbon-based esters, and it begins with protonation of the C double bond O. So it's very likely that that's what's going on here. Unfortunately, I wasn't able to find what I would consider to be a good definitive answer in what few textbooks and reference books I have available to me at home at the moment. But let's say it does make some sense. So let's have a look at how it would work. It may or may not work exactly this way, but we can rationalize that it's going to be close. What we're doing is making the osmium more accepting of a weak nucleophile. So here we are. Again, we're not touching these yet. And and we now have something like this, where we have now a cationic oxygen. Now, if we look at a resonance structure here, we could think about maybe this type of thing going on if I break that, ending up something more like this, so that I have now, look at it as being possibly something like this. Now, is this exactly what's going on? I don't know that for certain. But we're looking for something that's going to make a little bit of sense, and this is not a bad rationale. So if that is what I'm seeing, then this would be fairly logical and analogous to what happens with a carbon ester, that we have something like this, again, where either as resonance or as something fairly direct here, we have water then able to attack that cation. So it could either happen as part of the resonance or it could happen after it, what I'm drawing here. And if that happens, we end up here. So there are probably more direct ways to draw this, but I'm trying to get something drawn here that's reasonably close to what you would draw for a carbon ester that you'll see in more detail next semester. So I don't want to throw you off of what you're going to see eventually. Now, some of what I had seen here in possible explanations showed kind of an odd transfer of a hydrogen from here to here. I'm not sure I believe that. That would be a four-member transition state. I'm not a big fan of those. They're not impossible, but they're definitely unlikely. More likely it involves yet another molecule of the hydronium ion and water acting as a base here as separate steps. But either way, we would end up something like this. So we now have this, and we would have this one now protonated, which turns it into a reasonable leaving group, where it wouldn't necessarily be that any other way. So if I did this, now I would have something like this. And I could say, well, I could, for instance, use something like water as a relatively weak base, but again, we're dealing with metal, so that's not unreasonable. And then that would give me a driving force to displace this. So if I did that, I'd have one of those two oxygens now loose and be on my way to repeating the cycle to getting rid of the other one. And that's most likely what happens, is something along those lines. But the point is, I don't like half explanations, and this is one of those cases where your book tends to do that, and I'd like for you to have something a little bit better to look at. I'm not going to beat you over the head with this in terms of an exam question, but I do think you should see a reasonable explanation for how things happen as we go along, because understanding how this works is very similar to what's going to happen with carbon esters. You're going to do in a lot more detail next semester. So our leftover here would be the osmium with two double bonds and two OHs. So that's my osmium 6, which then the N-morpholine N oxide will have to take care of that, getting us back to osmium 8. So then this would continue along to, with the NMO being reoxidized to give me back osmium tetroxide and go back into the cycle. This is all a one flask reaction. This is not isolate one piece and then take it on to the next reaction. All of these reagents are going into this flask together. What I'm pulling out of it is a diol that is in syn stereochemistry and the catalytic amount of osmium tetroxide. I can demonstrate that because the reaction still works very well with very, very little of it present stoichiometrically. So it's the first example we've dealt with of a cycloaddition. It's also the first example we've dealt with of a reagent that is truly catalytic, that is regenerated during the reaction and then reused for another molecule of the same reaction, occurring again and then again and then again.